Hello, welcome to my ME 170 final video. Firstly, I should note that I used the control system designer in MATLAB for the plots only because I liked how it showed the bode plot, the root locus, and the step response all in one window, but I did not use it to manually adjust the poles to meet requirements as you can do so. And I proved that by putting my hand calculations in the appendix. So we're given G of S here, and looking at the bode plot, on the left, the root locus on the upper right, step response on the bottom right, we can see that clearly we have an unstable system. Step response goes to infinity, which definitely isn't what we want. And so we're given 4 requirements. Firstly, for a unit step input, we want the percent overshoot to be less than 30%. We solve the percent overshoot equation for the damping ratio zeta to find that zeta should be greater than 0.358. And this gives us this white range here. So I did trial and error with many different zeta values and found that higher damping ratios got me closer to meeting all the requirements. This makes sense since the higher zeta values decrease overshoot and increase the phase margin, which is what we want. In the end, I took the damping ratio equal to 0.7. Second requirement is the rise time less than 0.15 seconds. And we solve this equation here for the natural frequency omega n using the zeta from above. And this gives us omega n should be greater than 14. So I take the natural frequency equal to 15 radians per second. We won't worry about the other requirements for now. We'll just focus on these two because we want to design a lead compensator using the root locus method with the poles at locations corresponding to that natural frequency and damping ratio value. So plugging them into the equation here, we get S equals negative 10.5 plus or minus 10.79. If we just try changing the gain, then it won't give us those poles. So we will take the 0 value of the lead compensator directly above or below the magnitude of the damping ratio times natural frequency, which is 10.5, and we substitute that into the equation for sigma z here. And now we want to solve this equation at S equal to SDP. So solving for the phase gives us the pole location at 151.9, and we want to double check that alpha is greater than 1, which it should be for a lead compensator, and it is. That's good. We solve the magnitude equation of this, and we find k is equal to 3126. Therefore, we have our first lead compensator. GC1 is equal to 3126 times S plus 10.5 over S plus 151.9, right here. Now we'll take the loop function of that, which is the lead compensator we just found, times the given G of S, which is written here. And we're going to plot it to see if we met the requirements. If we look at the phase plot, we can see that the phase margin is 54, which is slightly less than our requirement, so that isn't met. If we look at the root locus, and if we pay attention to these highlighted points here, you can see that they're roughly at negative 10 plus or minus 10i, which if we go back here was our desired locations, so that's good. Now the step response shows us that the rise time is equal to 0.046, which is less than 0.15, meeting the requirement. And our final value is 0.959, which gives us the steady state error equal to 1 minus that, which is roughly 0.04, meeting our requirement of less than 0.1. Looking at the step info, we see that the overshoot is equal to 31, which is just barely above our requirement. So currently we have the 2 requirements met, which is the rise time and the steady state error, and we still want to satisfy our overshoot and phase margin, and this is what we currently have. So since we want the phase margin above 60, I will add another lead compensator since we want to add roughly 6 degrees of phase, which is shown here. and I'll take a safety margin of 6, giving us 12 degrees. So solving the equation for alpha, we find alpha is equal to 1.5. Again, double check that it's greater than 1 for a lead compensator. It is, and I'll take alpha equal to 2, rounding up. So we add the max phase at the crossover frequency from above. So we can see here that the phase margin occurs at crossover frequency of 22.8. So 22.8 becomes our omega m value. Therefore, using this equation, we can easily solve for tau, and that gives us 0.031. Now we find the desired locations of the pole and 0. The pole location is inverse of tau, which is 32.2, and the 0 location is 1 over tau times alpha, which is 16.1. And you can see that this is half of the pole location, which is expected since we took alpha equal to 2. So that gives us the second lead compensator equal to s plus 16.1 over s plus 32.2. Again, we're going to take the loop function and plot it. So it now becomes first lead compensator times second lead compensator times given g of s, which is written out here in numbers. Don't want to bore you by reading it all out. Looking at the plots, if we look at the phase bode plot, we see the phase margin becomes 65.4, which is greater than 60, meeting our requirement. The rise time remains below 0.15, which still satisfies the requirement. And our final value slightly decreased to 0.921, but that means our steady state error is 0.08, which is still less than 0.1, also satisfying the requirement. And if we look at the step info, we find the overshoot equal to 29.36, which is less than 30%, which is our requirement. Therefore, we have satisfied all 4 requirements: percent overshoot, rise time, steady state error, and phase margin with this loop function here. So again, this is just G1 of S, the first lead compensator, times the second lead compensator, times the given G of S. Now, the bode plot above here tells us that we have a stable loop, but we will just double check using the Nyquist plot. So you see that the phase margin is 65.4, the same as the phase margin on the bode plot, which is expected, just making sure we plotted the right functions. And then it tells us that it's closed loop stable, but we will use a Nyquist criterion just to really make sure. So we count the number of encirclements around -1, 0, which is in the middle here, this red cross. We have 1 encirclement, and then we have the outer encirclement, both counterclockwise, giving us n equal to -2. And from the given G of S, we know that we have poles at 0.5 plus or minus 3i. Therefore, we have p equal to 2, which is the number of positive poles. Therefore, z is equal to 0 since n plus p equals 0, confirming we have closed loop stability. Now, in terms of sensitivity, this is the same Nyquist plot, just zoomed in, so you can see -1, 0 better. And the closest distance that the Nyquist is to -1, 0 is this right here, which is our max sensitivity. And it's relatively high, which isn't good. It means that a slight change to the loop function would likely make our system unstable. But nonetheless, we have met all the requirements. We just need to make sure not to make any adjustments to the loop function and keep it as is. That concludes my report. Thank you for watching and listening. Have a good day.